Here's just a tiny short little video to tell you about power. Power is just the rate at which work is done. Okay, so it does have to do with work. So it's just work divided by time. So how much work was put in divided by how much time it took to do that, and then you have power. And so you've actually probably heard of the units for power. They're watts, right? That's usually how we measure light bulbs and how much, light gives off of a light bulb, where it's basically saying how much work are the electrons that are flowing having to do over per a unit of time, which is usually per second. Okay, so that's what power is. So it's very closely connected to work. So here we go. Here's our equation. It's doing it again. Just can't handle me today. So there we go. There's power is equal to work over time, and that is also on your data sheet. So yeah, look for that. However, we know work has sort of another definition, right? Because work can also be the same as change in energy. If there's a change in energy, then work has been done. So that energy divided by time could also get you power. Okay, so remember, there's a few ways to calculate work. So it could be there's a change in energy happened, and then that's work, and then you divide it by time. Okay, or of course we know work. Another way to calculate it is force times displacement. So if you have the force and the displacement, and calculate force times displacement, put it over time. Also, look, it's your favorite equation in there. It's the equation that everybody wants to use, but only we should ever use when what? It's moving at a constant speed. So if something is moving at a constant speed, then that power is really saying, oh, well, this is force times velocity, because velocity is d equal over t, right? So there's yet another way that we can calculate power. Okay, so just a few different ways for you to look at power, because it has a lot of different, since work can be defined in so many different ways, then we can define power in a few different ways as well. Okay, so this is how we would calculate power of a light bulb, like the wattage of a light bulb, because we want to know how fast are the electrons going around the filament, multiply that by the force that they're experiencing, and you have the wattage or the power of a light bulb. Let's do one example. Pump is to lift 8 kilograms of water per minute through a height of 3.5 meters. What output rating, i.e. watts, should the pump motor have? Okay, so we know power is work over time. We don't have work. We have nothing about work here. Oh, but I do have a change in energy. What's doing? It's lifting. That means it's giving it gravitational potential energy. So really, I'm going to look at the fact that power is a change in energy over time. Okay, and what kind of energy is changing? It's getting gravitational potential energy, so that's mgh, and what is happening over a certain amount of time, then okay, great. So I want to know what output rating should the pump motor have. So we know that this is happening per minute. So this is happening every minute. So we need to, then our time would be 60 seconds, because we always need time in seconds, okay? But again, it's lifting up 8.00 kilograms of water. And we know it's working against gravity, gravitational acceleration, 9.81, up to a height of 3.50 meters. And it's doing that every 60 seconds. So there we go. That's how we're going to get our power. And that is equal to 4.58 watts. There you go. That's power. That's all I got for you. Can you believe it? It's like the shortest amount of time I've ever talked for.